In this video, we are going to be covering the steps and examples of graphing quadratic functions in vertex form. For starters, we have a general version of this form of quadratics. Y equals, or f of x equals a times the parentheses x minus h squared plus k. On the picture we're looking at in front of us, we are basically comparing in blue the parent function of quadratics, just x squared. And then we have the equation in red, y equals x minus 1 squared plus 2. So we're trying to figure out what is different about these two functions. So the main thing that jumps out to me is first, the red function is being translated to the right by 1 space and then translated up by 2 spaces. By visual inspection, it doesn't seem like our function has been dilated at all by it getting bigger or smaller whatsoever. Or in layman's terms, you might call it skinnier or fatter or flatter and stretched, however you want to put it. It doesn't seem like it's been dilated at all. And we can compare them that the a value in the front of x squared and in the front of these parentheses there's just a 1 there, and it's just not included because of that being a 1. Basically, the difference is that we have translated right 1 and up 2 from the origin. A lot of information here that is going to be important for you to write down in notes. So the general version of our function we mentioned earlier, f of x equals a times x minus h squared plus k. The h comma k is going to be the vertex of the parabola. And the vertex is the main thing that we are getting from this form of a quadratic. In a later class, we'll be learning how to go back and forth between vertex form and what we did last week, which was standard form. When written in vertex form, the h comma k is going to tell you the vertex, and the h, as you may have guessed from the first slide we looked at earlier, that is going to take care of horizontal translation from the origin, or 0, 0, and the k is going to take the place of vertical translation from the origin. The axis of symmetry from when we graphed standard form last week can be obtained from this form as well. It is just going to be whatever that h value is going to be. Key points about this is that when you have that k value, is always going to be whatever that k value is, that's the y part of your vertex, or the vertical translation that has occurred. But the h is pretty much always going to be the opposite. For example, if you look at the bullet point right here where I was just highlighting, so this 1 right here, that means the h is 1 even though it's being subtracted here. So you got to think of it as x minus 1 instead of x and negative 1. And if it's x minus 1, that means that h is 1, and it would be moving to the right by 1 space. And then k would be a 5, and we wouldn't have to worry about anything. Compare that to the bullet point underneath it, where we have a positive 4 here and a minus 6. Because h is going to end up being the opposite, h is actually going to be a negative 4, meaning that it would go left by 4 spaces, and k is going to be negative 6, meaning it went down by 6 spaces. The a values here are going to be the same as they were in standard form. If that a happens to be a negative number, that means the parabola is going to be reflected downwards or have a vertical reflection. If a is a number bigger than 1, the parabola would be dilated larger. And then if it's a fraction between 0 and 1, or a decimal between 0 and 1, the parabola will be dilated smaller. Like I mentioned earlier, when you're saying dilated larger, some people refer to that as the parabola being stretched upwards or stretched downwards, and it's going to be skinnier. And then for dilated smaller, you might say that it is flatter, or it is closer to its x-axis if it happens to be there. Keeping in mind that a can be negative and dilated larger, and a can be negative and dilated smaller. That's kind of a separate thing compared to whether it's being larger or smaller, whether it's upside down or right side up. To walk through the steps really quickly of this process, we have an example. Basically, you're starting out in vertex form, and you can see an example right here of that. We want to take out the h and the k. In this case, we have a 2 and a -4 from our equation, and that gives us our vertex right away. And we know that our line of symmetry goes right through the vertex for every parabola. And that would tell us here that our axis of symmetry that we could draw in would be at x equals 2. For step 4, we are looking for 2 points on the one side of the axis of symmetry or the other. Usually it's a good idea to kind of pick the side that the y-axis is on, so you can then find your y-intercept as one of those points. And using x equals 0 right here is always a good idea, because that's going to be the easiest way to get a point. And then you just got to pick one more. Usually you want to pick a nice round number, a nice whole number, or an integer of some kind, I should say. In this case, they picked 1 as the other value, so it's just substituted in for the x in our equation, and then that both of those are evaluated to get 1 point at 1, -1, and then our y-intercept of 0, 8. Finally, because our parabola has a line of symmetry, we can just reflect these points across that line of symmetry and get our other points. Generally speaking, if you want to graph a parabola accurately, usually you want to have at least 5 crucial or important points in order to get that drawn as correctly as possible. And you can see that that has been done in this example. Now we're going to work on graphing some vertex form examples. In some of these, we'll be looking at functions that don't have every single part of vertex form, and that will be good practice as well. For instance, in this problem, we don't have the a value in the front, and we also don't have a k value. So it would be my recommendation to write a problem out again, kind of as like x minus 2 squared here, and then have it as plus 0. So the first thing that I would do here, and to remember our steps, we're going to identify our vertex. So since thinking back to our example, we know the opposite of this 2, this -2, and then the 0 together would mean that our vertex is at 2, 0. So we can plot that point right here at 2, 0. And we can draw our axis of symmetry all the way down through this point. So that already is basically the first three steps of our process. So now from here, we want to think about how to graph some more of the points. So like I mentioned earlier, finding a y-intercept would be a good idea to start with. So we could put in 0 minus 2 squared, and that would give us an answer of 4. And so that means that we have 0, 4 as our first point, 0, 4 being right up here. And just like our last example, we have an x equals 1 right here that we can use. And so I'm just going to do 1 minus 2 squared to get that point, and that is going to be equal to positive 1. And so that means I have 1, 1 as my point, and I can mark that as well. We need to use our symmetry to plot our points. So if I reflect this first orange dot, that means I would have an opposite of there, and then I can reflect my higher up point so that I can have that there. And we'll see how accurately I can draw a parabola curve using a mouse. And that looks pretty good to me. And we have our parabola graphed. Moving on to problem number 2. We have x squared minus 4. So like before, I'm going to write this as the full version of it first. So I have 1 times x minus 0 squared minus 4. First step will be to identify our vertex. So we have a 0 and a minus 4. So our vertex is 0, comma, -4. And we can plot that point right down here. Our axis of symmetry, and we can even write axis of symmetry is x equals 0, right at our x part of our vertex. So I can draw that down the center of my graph right here. I need to find a point on each, at least one point on each side. So maybe what I will do is find +1 and +2 to make it easy on myself. So I basically am going to do 1 squared minus 4, and that is going to be 1 minus 4 is equal to -3. So I have the point 1, comma, -3, and I can plot that. And then I'm going to pick x equals 2. So I can do 2 squared minus 4, which equals 0. And now I can plot the point 2, comma, 0 right here. And my last step for this problem would be to graph the reflection of these points. So my bottom point would reflect to this red point right here. My top point would reflect to my red point right here. And then I can draw my parabola through all 5 of these points semi-accurately with my mouse. And that is the graph of f of x equals x squared minus 4 using vertex form. Now we're looking at a problem that has more of the process, more of the whole vertex form involved. It just has a 1 in front. So we can just skip right to our vertex. As we know, it's the opposite of our h, -2, and the same as our k, -1. So -2, -1 would be right here. And that means our axis of symmetry is going to be right through that vertex, going all the way up our graph in blue right there. Our next step is finding more points. So I'm going to pick here -1 and then our y-intercept. So let's do -1 first. So that would be -1 plus 2 squared minus 1 is going to be -1 plus 2 is 1. 1 squared is 1. 1 minus 1 is 0. So that point that I would have here is going to be -1, comma, 0. So maybe plot -1, comma, 0 right there. And then I'm going to plot my y-intercept. So that would give me, I would put a 0 in for x. No, 0 plus 2 should be in the parentheses. And we're going to square that minus 1. So I would have 2 squared is 4 minus 1 is 3. And that means I have my y-intercept as 0, 0, comma 3. 0, comma 3 is the point I got from that. So 0, comma 3 would go on our graph right there. And we can reflect these points. And I can reflect my top one right directly over. And then I can reflect my bottom one directly over as well. And I can draw my parabola through these points like so. And then the right half would be a reflection of that as well. And that wraps up the function f of x equals x plus 2 squared minus 1. Next problem is a little different. We have a 1/2 in the front. So if you think back to before, well, this is going to be dilated by half compared to some of the parabolas we've been drawing so far in this video. And so we want to start by identifying our vertex. That is easy as just 3, 1. And so we can plot 3, 1 right here. And we can draw in our axis of symmetry right down through the middle of that vertex. So we got that dotted line already done. And we're going to use our points kind of to the left here. So we're going to put a 1 and a 2 in here. So to put it, when you do x equals 1, we're going to do 1/2 times 1 minus 3 squared plus 1. So we have 1 minus 3 in parentheses. That equals -2. -2 squared is 4. 4 times 1/2 is 2. 2 plus 1 is equal to 3. And that means we're going to plot the point 1, 3. So 1, 3 would be right here. And then we're going to do x equals 2 right next to our vertex. And so I'm going to do 1/2, 2 minus 3 squared plus 1. And since there's a fraction involved here, you could put this right in your calculator, but we can do this just in our heads, I'm sure. 2 minus 3 is -1. -1 squared is 1. 1 times 1/2 is 1/2. 1/2 plus 1 is 1.5, or you could use 1.5. So we're going to be graphing 2, 1.5, and having to do a little estimating here with our point. 2, 1.5 would be right about right there at that blue point. And we want to now reflect our points across our axis of symmetry for our first point and second point. And now we can draw our parabola through all of these points. And so you can see as the way I'm drawing this, that it has, you can kind of go through these to get those answers for what the graph would look like. I believe that leads us to our last one we're going to graph. Now we have -2 in front, so that's going to be a different sort of graph there. And so first, just like always, we're going to do our vertex. Opposite of this -1 is 1, and then 3 will give us it 1, 3 right here. And we're going to draw our axis of symmetry directly down through our vertex, the middle of our parabola. And we're going to use our y-intercept and -1 for this. So we'll plug in 0 for x to find our y-intercept first. And evaluate this expression with 0. So we have 0 minus 1 is -1. -1 squared is 1. 1 times -2 is -2. -2 plus 3 is equal to 1. So we have the point 0, 1. And so we can plot 0, 1 on our graph. And we're going to try -1 for our next x value that we're going to find a point for. So we have -1 minus 1 squared plus 3. So that'd be -2 in the parentheses squared, which is 4. 4 times -2 is -8. -8 plus 3 is equal to -5. So that means we're applying the point -1, -5. And that would be sort of off our graph, but we'll just put it right down here at the bottom. And now we just need to reflect our points across our green axis of symmetry. No, that wouldn't go there. That would go one space further over. It would go right here. And now we can draw our parabola, remembering that this 2 made it upside, -2 made it upside down and also dilated larger by 2. So you can see that this parabola is going down a lot faster than the parabolas we've done before in this video. In this slide, I want you to take a second to think about what kind of transformations happen to each of these functions 1 through 6. In number 1, we can see that the vertex would be at 2, 1. So that means it would translate to the right 2 and then up 1. Number 2 is only x squared minus 1, so that would be a transformation of down 1. Number 3, the translation would be to the right 2 because of that x plus 2 inside. So that would be to the left 2, actually, I meant. So that is translating left 2. Number 4 is just a negative sign in front of nothing else. That means it is just a vertical reflection. Number 5 has a 1/4 in front, so it is dilated by 1/4 and made smaller. The x minus 1 on the inside would move it to the right by 1 space, and the plus 1 on the end would move it vertically up by 1 space. And finally, number 6 would be dilating it 3 times larger and stretching it out, and then moving it left by 1 space because of the plus 1 inside the parentheses, and then down 1 because of the minus 1 on the end. And finally, our ending problem, we're going to look for the differences between the transformations of the graphs below when they're both compared to the origin. So our blue graph is 4 times more stretched. All those y values are 4 times higher up. It was moved right 1 and up 3 from the parent function. And then our red graph for function 2 has been dilated by half, so it's half as stretched, or it's kind of half as large of a parabola as the origin or our parent function might be. And then it was moved to the right by 3 spaces and then translated up by 2 spaces. And that concludes our video lesson on graphing the vertex form of quadratic functions. Thank you for watching.